I don't see anything at all that is better explained by saying we live in a simulation than we don't. If we saw, occasional miraculous deviations from the known laws of physics, I might feel different, but we don't. If we saw some fundamental resolution limit, or if our universe was very, very small and clearly optimized to conserve some kind of resource, then I might see a different point of view. But just as a Bayesian with certain priors, nothing that I see about the universe increases the likelihood that it's a simulation for me.
Hello, this is Robinson Erhardt and a thin sliver of Cornish Rex that goes by the name Pins, here with the introduction to Robinson's podcast, number 207. And this episode is with no stranger to the show, Sean Carroll, who is Homewood Professor of Natural Philosophy at Johns Hopkins University and Fractal Faculty at the Santa Fe Institute. Sean is also the host of the Mindscape podcast, which is a terrific show that covers philosophy, science, culture, and lots of other things besides that. And this is Sean's fourth appearance on this podcast. He joined David Albert of Columbia on episode 106, Slavoj Žižek on episode 118, and then Daniel Dennett and Steven Pinker on number 200. But this episode is just me and Sean and the aforementioned Cornish Rex that I have right here. And it's coming out in advance of Sean's latest book, Quanta and Fields, The Biggest Ideas in the Universe, which will be released on May 14th, which, let's see, it's the 10th, 11th, 12th, so it should be 2 days after this episode comes out on Sunday the 12th. So naturally, the book is what we talk about, though, because the focus of the Biggest Ideas in the Universe project, which we get into, is really to teach you quantum mechanics. We focus on more of the bigger picture ideas, as well as some of the philosophical problems surrounding them. But in addition to Quanta and Fields, the namesake topics of the book, we also talk about other things like the simulation hypothesis, string theory, the possible end of physics. And there's a link to Sean's book in the description, so you should definitely pre-order or order it depending on when you're listening to this. A few other things. Sean is a fellow of the John Bell Institute for the Foundations of Physics, along with half of last week's duo of Slavoj and Lee Smolin, namely the Lee Smolin half. And if you're at all interested in this sort of research and philosophy, then you ought to check out the JBI and consider making a donation, which is or would be very helpful at this point in the Institute's lifetime. And there's a link to that in the description as well. There's one clarification I need to make about something I said in the episode. So Sean and I talk a bit about the philosophy of mathematics, and I say quite imprecisely and confusingly something along the lines of Joel David Hampkins, who parenthetically is a quite renowned philosopher of mathematics at Notre Dame, who's been on the show a couple of times. I say that Joel David Hampkins believes concretely in the existence of mathematical objects, or he believes in their concrete existence, or something like this. And again, I was being very imprecise, and I don't want to be interpreted as claiming that Joel thinks mathematical objects are concrete or physical or something like that, but rather that he believes them to be in some metaphysically robust sense bona fide existing objects. Though you can listen to episodes with him if you want to hear more about this, or Sean says in the episode that they're already scheduled to talk, so you might hear more about it on the Mindscape podcast. Otherwise, reviews, comments, likes, subscribes, all of these things are extremely helpful. There is a Patreon if you would like a link to an ad-free RSS feed or some show notes. But other than that, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with Sean. I've got pins here, and you are also a friend to cats, and your new book in the biggest ideas in the universe series, Quanta and Fields, is dedicated to one of your cats, Ariel.
It
And
is,
the
yes.
first question is whether or not she was a good contributor and a better contributor than Caliban.
Caliban, if he plays his cards right, will have the third book in the series dedicated to him. So it just worked out pretty well. Sure, they contribute. They contribute peace of mind and occasional happiness for me. Sometimes lack of peace of mind. That's always true. But very, very glad that Ariel and Caliban are around. They deserve some credit for whatever happens in the book.
Yeah, I saw that Jennifer, the dedication to the first book in the series was to Jennifer, so Caliban was missing out. My cat is actually, I think, pretty important to my work because it's nice to not always be alone and to have somebody when I'm writing. But before these podcasts, I always try to dose her with her favorite cat food so that she'll go into a food coma. But today it's not working. She's already knocking things over and running around.
Ariel and Caliban do not like the voices coming out of the computer, so they do not bother me while I'm broadcasting. It's a big house, they can go somewhere else.
Well, turning to Quanta and Fields, I've read plenty of popular physics books for the show, but none that got so deep into the math behind the physics. And it just raises the question, I mean, why are you writing the biggest ideas in the universe series like this?
Yeah, so for those folks who don't know, the biggest ideas in the universe was based on a set of YouTube videos that I did, and they're still up on YouTube. You can check them out. They started during the pandemic as a way to explain some big ideas in physics. And, my original idea was to talk for 15, 20 minutes about some concept. And I ended up talking for an hour and a half because that's, tends to be what happens to me. And so I did all this work. And so why not turn it into a book? Of course, a book is a very different thing. And so it's almost rewritten entirely. There's not that much relationship to the videos. But the thing about the videos that was different was I figured, why do yet another popular science explaining of things that people have heard of? What could be different about it? And I realized that, we always talk about how physics speaks the language of mathematics, and it can be a bit of a barrier to people truly understanding what's going on since they don't know the math. And the math can be hard. I have no illusions about that. But when you're a professional physicist, of course, you learn the math, but you learn it in a certain way. You learn it because you want to solve the equations. Here's Schrodinger's equation. We'll explain to you what it means, but also we'll teach you how to solve it so you know what the solution looks like for the hydrogen atom, the simple harmonic oscillator, or whatever. And in fact, most of your actual effort when you're taking these physics courses is solving the equations, doing problem sets, watching the professor solve it on the board, taking exams or whatever. If you eliminated that step, if you said, I'm not trying to train professional physicists, I just want people to understand the ideas, then I think you can actually present the equations and explain what they mean in all of their glory, exactly the same equations that a professional would look at, but just explain what they're talking about. I did that in volume 1 of the biggest ideas, which was called Space, Time, and Motion with classical mechanics and relativity. So volume 2 is trying to do that for quantum mechanics and quantum field theory. Whether I succeeded or not will be in the eye of the reader, of course.
I think it was a success, a resounding success, and hopefully we'll get back to just what it means to say that physics speaks the language of mathematics. But obviously, I mean, the book is the place to go to learn the physics of quanta and fields and the mathematics behind it. And we will get into quanta and fields in particular. But the book raises a lot of philosophical questions that, since this isn't your purpose, you don't answer. And one is about this interesting tension between using quantum mechanics and understanding quantum mechanics. And I've got a few quotes from the book pulled up. So I'm going to quote you here. And it is, the truth is that physicists themselves don't agree on what, at rock bottom, quantum mechanics actually says.
the top quantum physicists in the world don't agree on what is going on to produce the results they predict and observe so successfully. And I think a good naive understanding of what science is the attempt to understand the physical world. But how do you see the purpose of science if our best physicists disagree about what quantum mechanics is? What's going on in a physics department or within physicists' heads that they don't care about the interpretations or what a theory really says about reality over and above its predictive abilities?
Well, that is a wonderful question, of course. And again, just for the folks who don't know, I wrote a whole book about the foundations of quantum mechanics and what it's supposed to mean. But that was a previous book, Something Deeply Hidden. And my self-proclaimed purpose in the Biggest Ideas books is to not talk about anything controversial. I will allude to controversy and speculation and whatever, but I really want to stick with the ideas that we all agree on. So like you say, the foundations of quantum mechanics are not a set of ideas that we all agree on. Now, to me, that is just incredibly embarrassing, both that we don't agree and that we don't even try to agree, that it's not considered a high priority thing within physics to try to understand what quantum mechanics is really saying. And if you're not a physicist, you might say, well, how in the world can they get away with that? And the answer is we have this sort of cookbook of rules that says, in this situation you do that, in that situation you do that. And they apply pretty well to the situations that we're very familiar with, setting up an experiment in a laboratory, making some particles collide, watching what comes out. We can predict the outcomes of those experiments using the rules of quantum mechanics, even though they're sort of ad hoc and thrown together, to enormously good accuracy. It's an amazingly effective theory, even though we don't agree about what is really going on. So that's kind of amazing. I mean, it's amazing you can do that well without having a very deep understanding. The problem is, of course, when you want to go beyond the simple setups that you understand, when you want to ask about the origin of the universe, for example. The rules are not clear, and the different choices that you might make turn out to be super duper important. Now, I think that I don't know this very well. I don't have a historically informed sense of the question about why the physics community as a whole allowed this situation to go on as long as it did without understanding quantum mechanics. There's famously these debates in the late 1920s, early 1930s between people like Einstein and Schrödinger on one side, people like Bohr and Heisenberg on the other, about whether or not we understood quantum mechanics and what it really meant and so forth. And as a matter of historical fact, Bohr and Heisenberg resoundingly won that debate. I'm happy to be on the side of Einstein and Schrödinger. I think that's actually not too bad, but they lost the public relations battle by a lot. And I suspect there's a couple things that are going on. One is that there were other things to do besides think deeply about the foundations of quantum mechanics, right? I mean, 20s and 30s into the 40s and 50s, not only were there wars being fought, but incredibly difficult questions were being asked about quantum field theory and particle physics and physics more generally. So there were like things you could put your fingers on and then do experiments about them. And physicists always like that kind of thing. And the other is it was just unclear how to make progress. If people had different ideas for different theories that would underlie quantum mechanics, how do you test them? How do you know which one is right? And so that's a weird spiral. Maybe we don't know how to test them because we haven't tried to think about it that much, but we haven't tried to think about it that much because we don't know how to test it. And, let's give it an analogy. General relativity, Einstein's famous theory of gravity, was largely ignored in the middle of the 20th century. Even though everyone thought it was right, they didn't know what to do with it. There was no observation or experiment that they could do that really helped you understand it. So it wasn't taught in graduate schools. It was there. We knew that it was a good theory, but no one really specialized in it or anything like that. Physicists are relentlessly practical people. Tell me what you can do, and they will follow up on that.
Mm-hmm. Yeah, speaking about avoiding controversy, I was surprised that there was not more about the Everettian theory of quantum mechanics in the book, which we talked about at length in our episode with David Albert, or even quantum gravity, though string theory gets an honorable mention when you're talking about the origins of string theory and modeling the strong force through strings. But is this where you see sort of the role of philosophers in physics now, is trying to get past our capacity to merely use quantum mechanics, but to disentangle these conceptual questions in the way of our understanding?
I think both physicists and philosophers have a huge role to play here. I mean, philosophers have certainly kept alive these set of questions, and they've helped us understand why some of the proposed solutions just are not going to work. I think that philosophers are better at telling physicists where they're not making sense than they are at proposing better theories. So I suspect, I'm happy to get good ideas from anywhere, but I suspect the better theories are ultimately going to come from physicists because that's what they're really trained to do. And the philosophers can help them understand why this is just not up to the task when they don't quite do the right job.
So Stephen Hawking is, well known for having a distaste for philosophy, and he wrote that philosophy is dead. And then there are others like Neil deGrasse Tyson or Lawrence Krauss, who I spoke to recently, and I could tell was kind of irritated by my philosophical questions, who have these very negative feelings about philosophy. Do you have any sense of just why so many physicists, and maybe I'm generalizing too much by saying so many physicists, are so hostile to philosophy? And before you answer, one thing that I took from my conversation with Lawrence is that he thinks philosophers spend way too much time worried about quantum mechanics and these debates of the 20s and 30s as opposed to quantum field theory.
Yeah, sorry, what was the first part of that question? You added an extra question on there.
Yes. Why do you think that so many physicists are hostile to philosophers of physics or philosophy?
Well, I think that physicists are hostile to anything that isn't physics more often than not. The philosophers should not feel picked on. We physicists will pick on economists and historians and sociologists just as well. Don't feel bad, or even mathematicians. Mathematicians get some grudging respect because they're useful to physics, but they're largely wasting their time proving things from the point of view of the physicist. So, again, relentlessly practical. Show me the money. And I'm not saying my point of view here now, but you asked why do most physicists think this way? What's it going to get me? For most physics questions, philosophy has no special way of helping, right? If I want to do an integral, if I want to figure out how to evaluate a Feynman diagram, I do not turn to a philosopher. The questions where philosophy is very helpful, things like the measurement problem in quantum mechanics, the origin of the universe, questions of naturalness and fine-tuning and so forth. These are exactly the questions that physicists are kind of awkward about. They kind of get nervous talking about them because they don't know how to answer them. They don't know what experiment to do to figure out what the answer is. So there's sort of a mismatch in style, and they can both get along perfectly fine without each other in their own minds. So until philosophy tells physics something that is really, really useful to physics, then physicists are just not going to pay it a lot of attention.
Is, quote unquote, solving the measurement problem particularly relevant to quantum field theory or the standard model of particle physics as it is empirically used or empirically confirmed, or something like quantum gravity? Because, as I said, Lawrence Krauss seems to think that no one cares about this but philosophers, and for good reason. And I talked to Eric Verlinde about string theory, and he seemed to echo this. He just wasn't at all interested in the interpretations. But then other people working on quantum gravity, like Faye Dowker, says that the path integral is quite vital to the program of causal set theory.
Yeah, I think that our mutual friend Dan Dennett, who passed away recently, has said things along the same lines as what I'm about to say, which is that you can't help but do philosophy when you're doing science. You can only do it well or do it badly, right? There's plenty of physicists who ignore philosophy, but they're constantly making philosophical pronouncements. They're just kind of silly ones. They're not very educated ones, not very thoughtful ones. Again, that's fine for a lot of areas of physics. For quantum field theory, when you want to predict the electric dipole moment of the muon or something like that, Why in the world do you need to think about philosophy to do that? But on the other hand, quantum gravity, emergent space-time, things like that, these are precisely areas where philosophy might be super duper important. Cosmology overall, with things like the anthropic principle. The anthropic principle, as deployed by many physicists, is exactly an example of philosophy done badly because they haven't really thought these issues through. So I think it just depends on what you're interested in. If you're a physicist who doesn't like philosophy and you stay away from those questions and areas where philosophy is important, I think you can be fine.
While we're on the topic of use and understanding in regard to physics, and before we actually turn to some of the physics in the form of quanta and fields, I wanted to talk a bit about scientific realism. And for our listeners who aren't familiar with this debate, it's one of the biggest debates or topics in the philosophy of science. It's the question of whether we ought to be committed to the existence of the objects or structures postulated by our best scientific theories. And historically, I think, and maybe you can weigh in on this, but the strongest argument for having commitments of this sort goes back to Hilary Putnam and is called the no miracles argument. And it holds that it would have to be some sort of miracle for the predictions of, say, the standard model of particle physics to be observed to the degree of accuracy that they are without the standard particle model being at least largely true. But then, on the other hand, the best argument against it is known as the pessimistic meta-induction, which holds that basically if all of our best theories have been false in the past and we've had to throw out those either object-based or structure-based ontologies, is it rational to have any credence that our current ontology is right? So in general, where do you see yourself in this debate as it relates to quantum mechanics, or maybe more particularly the standard model?
Well, I think that there's two separate questions. One is, within the way that we think about any one theory, does the best way of thinking about that theory hold that you should treat certain parts of it as real? In other words, specifically what I have in mind is, in quantum mechanics, do you treat the wave function as representing reality? Some versions of the foundations of quantum mechanics say yes, some say no. That's just purely within everyone agrees on quantum mechanics, right? But we're disagreeing with what parts of it are ontologically relevant. There's another question. I think it's a separate question to ask. Okay, but you don't know that quantum mechanics is right? I mean, that's the question about meta-induction. And you might say, well, why bother thinking that wave functions are real if someday wave functions might disappear because quantum mechanics is no longer right? And for the latter question, I think that structural realism essentially solves it for me. The idea that what is real and what is not going to go away are certain patterns, certain structures in our theories that have been empirically verified. Newtonian mechanics has a different ontology than general relativity does. But apples still fall from trees in both Newtonian mechanics and general relativity. So it's okay to attribute some reality to that phenomenon, even though the ontological explanation for it is completely different in these two different theories. I don't think anyone should claim to know the final ontology of nature and only be realistic about that. That would be very, very hard to pull off. But you can think that there is something that is the final ontology, even though you don't know what it is. And these structures that emerge at higher levels are what we are learning about through scientific practice. Now, in the question of quantum mechanics itself and the wave function, I agree with Putnam. I mean, the wave function is super duper useful in quantum mechanics. We really can't do without either it or some equivalent of it. So, of course, I think it's just very natural to treat it as representing part of reality. And it's a short road from there to believing in the many worlds interpretation of quantum mechanics, but we can argue about that. But I'll point out that in the book, this came front and center, even though my goal was to only talk about things everyone agrees on. I had to talk about quantum mechanics, and not everyone agrees on quantum mechanics, even though they agree with the final predictions. But the way that you talk about it along the way can be very, very different from person to person. So I made a I made an executive decision saying I'm going to talk about quantum mechanics as if the wave function is real. And if you don't like it, you can always translate it into your own way of thinking about it. But I can't, every time I try to say something about virtual particles, include 2 pages of disclaimers and caveats saying, well, different people will talk about them differently.
This is a good point for us to get into some of the physics just to make sure that our audience has a grasp on what we're talking about going forward. And I know that this is very basic, especially since we've been referring to it for the last 5 or 10 minutes, but restricting ourselves to quantum mechanics and not yet going into quantum field theory, though I know that that is part of quantum mechanics. Just what basically is the wave function?
Good. That might as well start there, I think. That's chapter 1 of the book, the wave function. And I think that it's a profound change in how we think about the world that happened starting in the year 1900, but the revolution was completed in the 1920s. And the simplest way to skip over all the missteps along the way is to say, when we had classical mechanics pre-1900, if you were Isaac Newton, you would say, if I have a collection of particles, for example, I can talk about the state of those particles, the physical state, and that physical state is defined as the information that I need to know what the particles are going to do in the future and to know what they did do in the past, right? I need the positions of those particles, and I need the velocities or equivalently the momenta of those particles. And then the laws of physics, if I know what kinds of particles I'm talking about, so I know their electrical charges and masses and things like that, the laws of physics tell me how they develop over time. And quantum mechanics comes along and says it's radically different than that. Like this, it's amazing how different quantum mechanics really is. And this is part of the reason why even physicists have trouble facing up to what quantum mechanics says. It says, for one thing, if I just have one particle, I don't have a position and a momentum for that particle. I have this thing called the wave function. And the wave function can be expressed in different ways, but it's easiest to think of it as literally a function of position. So everywhere the particle might have possibly been, there is a value for the wave function. In a typical situation where like the particle we're talking about is an electron in a hydrogen atom, and you have a picture in your mind of the orbital of the electron in the hydrogen atom, that orbital sort of stretches out to infinity in principle. It fades away, but very, very, very quickly, actually, but never quite gets to zero. And that represents the wave function. That is a picture of the wave function of the electron. And I forget if I said 2 things, but there's really 3 amazing things going on here. So the ontology is completely changed. Number 1, you went from a particle with position and velocity to a cloud, right? A wave, a function of space, the wave function. Number 2, you can never see the wave function. We're going to get to that. We talk about measurements, but when you look at it, you don't see it. And that's why it's legit to worry about whether the wave function is real. Why are you demanding reality to something that I can never even see? That seems a little bit fishy. But then third, when you have 2 particles, you do not have 2 wave functions. If you did have 2 wave functions, that would be saying I have the Greek letter psi is the variable usually used for these kinds of things. So psi of x would be the wave function of a single particle. If you thought that when you had 2 particles, you had 2 wave functions, you might imagine having psi 1 of x, which is the wave function for particle 1, and psi 2 of x, which is the wave function for particle 2. But quantum mechanics says, no, that is not what you have. You have one wave function as a function of 2 variables, the 2 possible places I could observe, particle 1 and particle 2. So instead of psi of x for one particle, for 2 particles, I have psi of x1 comma x2. So it's not even a wave. It's not even a field in the usual sense, like the electromagnetic field or the gravitational field. These are fields. They have values at every location in space. The wave function does not have values at every location in space. It has values at every possible set of observational outcomes. If I were to look for the 2 particles, then I would be able to see the probability that they're here and there in different places. That's what the wave function tells me. So it's a very abstract, very completely different thing. And that's why physicists are still struggling to come to terms with it.
You have said about 20 things that I could ask questions about, but I will start with one thing that you said a few minutes ago. I mean, even before this response, you questioned whether we should think of the wave function as representing reality. And I think there's a deeper question here. I mean, one, what it means to represent reality, or versus the wave function, I mean, being reality. And you also said that you can never see the wave function. So one, a function, at least mathematically construed, is just a set. It's typically thought of as a set. But then on the other hand, I had another guest on the show, Carl Wyman here at Stanford, who was the first person to isolate a Bose-Einstein condensate. And he said that the way that he described it is when you have this Bose-Einstein condensate, you are looking at a wave function. That is how he describes it. So the question I have, I guess, is whether the wave function is meant to be something that represents reality, or is it something that is real itself that you can observe?
I'll be honest, I don't think this is a very sensible question to ask. I know why people are tempted to ask it. Is the wave function real, or does it represent reality? I don't know what the difference is between those two things. Like, it's a function. What does it mean to be real? You know, like it's the mathematical way we describe reality, by which what we mean is if you set up reality in a certain way and you let reality go, then you make a prediction for what you're going to observe. I can construct that prediction by setting up a certain mathematical fact, the value of the wave function at different points in space. I can evolve it using a certain equation, and then I can do a certain procedure to it to make a prediction. But reality is reality. Reality is not some mathematical thing we invented. Reality is sui generis. It's uniquely reality. The scientific question is, how do we model reality? How do we describe it? What is the language that we use to talk about it and make predictions? And to me, the wave function is part of that. As far as seeing the wave function, we can't do it. I think that Carl Wyman was just exaggerating a little bit for poetic purposes there. Of course, this is a problem due to the fact that physicists don't agree on what wave functions are or how they should be talked about in a very real way. In anyone's version of quantum mechanics, when you have a physical setup described by a wave function and you're going to make an observation, in the general case, sometimes you get lucky, but in the general case, the possible measurement outcomes do not include, here's what the wave function is. They include certain aspects of the wave function, and they might include different aspects that assign different probabilities to them. That's the fact of measurement in quantum mechanics, is that measurement changes the quantum wave function. That's not true in classical mechanics. You might think, well, in classical mechanics, if I want to take a picture of a planet, I need to observe the photons coming off of it, and so some momentum is leaving the planet. But come on, you can make that exchange of momentum as tiny as you want. You can observe things in classical mechanics as close as you want to not disturbing them at all. Whereas in quantum mechanics, no matter how hard you try, certain kinds of measurements are always going to disturb the system by a lot. That is one of the things that makes quantum mechanics fundamentally different.
One other thing you said that I just wanted to clarify is you said that you don't have two wave functions with two particles. You still only have one wave function. And what I wanted to clarify is whether this is the standard reading, that there is only one wave function. I know that that's maintained by those who adhere to the many worlds theory, but do the other interpretations of quantum mechanics also have only one wave function?
Any version of quantum mechanics that is realist about wave functions says there is only one wave function. There's one physical thing, the wave function of the system under consideration, and ultimately the wave function of the universe. There are approaches to quantum mechanics that are not realistic about the wave functions, that are, I shouldn't say realistic, I should say non-realist, anti-realist. So there, you can treat the wave function as a tool that individual agents use to make predictions. And one person might have different information about a system than another, and therefore they might assign a different wave function to the system than the other. But it's not that each individual subset of the universe has its own wave function. It's that each agent has the different wave function they assign to the whole universe all at once.
Okay. And then just so we can tie quantum mechanics and quantum field theory together, you've already said that a field is something that has a value at every location in space, but this doesn't really give a very intuitive conception of what a field might actually be like. So do you have a way of describing a field that makes it seem, I don't know, more physical, for lack of a better word?
There's lots of different ways, and I can give you a couple, but I will also just opine that you should suck it up. That you should really come to terms with the claim that what a field is something that has a value at every point in space-time. That's really what fields are. Don't let the metaphors or the analogies have too much of a grip on you. Of course, there are many of them. If you go out to the ocean or to a lake and you see waves on the surface, the height of the wave above the average water level is a function of where you are, right? That's a field. It has a different value at every point. In this room, if I go with a thermometer, I could measure the temperature at each point of the air in this room. That's a field. Anything that has a value at every point in space and time is a field.
As I said, towards knitting these two perspectives together, in quantum mechanics, the wave function governs particle configurations. What does it concern in quantum field theory? And do you think it's fair to describe quantum field theory as, the successor to quantum mechanics? Or you just subsume it under quantum mechanics?
Quantum field theory is a kind of quantum mechanics. It is quantum mechanics applied to fields rather than to particles. So in both cases, there's a wave function because it's both quantum mechanics. In the case of particle mechanics, the wave function can be thought of as a function of where you might see the particles, right? Psi of x1, x2, etc. If you have a field, let's call it phi, a different Greek letter, phi of x, okay, then it will have a wave function. But that wave function is now a function of every possible profile that field might have throughout space. So think of every possible field profile phi of x, not each value. Sorry, I keep bumping in. I'm getting too excited talking about quantum field theory. Not each value at each x, but all the possible values of the function phi of x, okay? The wave function of that field will assign a number to every possible function phi of x. And you can imagine in your mind that somehow you were able to observe that field all at once, everywhere, throughout all of space. And then the wave function of that field would tell you the probability of getting different measurement outcomes for that measurement.
Do you think it is fair to say that quantum mechanics has a fundamental ontology of particles and quantum field theory has a fundamental ontology of fields where particles can just be thought of as fluctuations in these fields?
I do not, because the fundamental ontology in both cases is the wave function. And the wave function is a vector in Hilbert space in an abstract way that John von Neumann explained to us in the 1930s. Again, quantum field theory is not different from quantum mechanics. It's just, let me back up a little bit and be more clear. When we teach quantum mechanics to our students when they're undergraduates, of course, they've heard about classical mechanics already, right? They know about balls rolling down hills and inclined planes and things like that. They know about Newton's laws and Kepler's laws. And so, of course, also because it went that way historically, it makes sense that we teach them quantum mechanics by starting with classical mechanics. And indeed, even very grown-up, very highly accomplished physicists will construct new quantum mechanical theories by starting with a classical theory and doing what we call quantizing it. There's a set of rules for going from a classical theory to a quantum theory. But that whole procedure is a bit of a fudge, to be honest. Nature doesn't do that. Nature does not start with a classical theory and then quantize it. Indeed, the whole idea of quantization is much less well-defined than you might hope. There's no unique map from classical theories to quantum theories. One classical theory could give you many different quantum theories. The map is not well defined. There could be different classical theories that give you the same quantum theory. There could be quantum theories that have no classical precursor whatsoever. So there's even classical theories that have no quantum theory associated with them. So it's just two different sets of things. And that's why, even though when we talk about particle quantum mechanics and field theory, it's tempting to think that this is a quantum theory of particles or of fields, and we're just describing it in a certain way. It's ultimately wrong to think of it that way. It's a quantum theory of quantum theory. That's what it is. And the quantum ontology is that of a vector in Hilbert space. And that's how nature thinks, and we should try our best to measure up to that.
Okay, so the fundamental ontology of quantum field theory is the wave function. And I'm wondering then, to get a better understanding of the structural realism position that you endorsed, how successor theories to the standard particle model might have us revise or retain this ontology. And before we get into that, since we haven't talked about the standard particle model and that, or the standard model of particle physics, and that's another huge part of quanta and fields, just what is the standard model?
Good. The standard model is a terrible name for the most important theory in all of physics. And it is not a beautiful theory in a very deep way. You know, when Einstein invented general relativity, not only was it the work of one person, 10 years of really intense work, but the result is just so simple and beautiful. And it's a pleasure to teach general relativity and to think about it, et cetera. The standard model is a mess. It came about over many decades of work from many different people, involves many different ingredients. The fundamental idea is that, you know, back in the 1920s or whatever, or earlier, we might have thought that particles and fields are two different kinds of things. We knew about the electromagnetic field. Maxwell and his friends had put together electromagnetism quite successfully in the 19th century. We knew about particles. We knew about electrons and protons and neutrons, et cetera. And so they were thought of as two different kinds of things. But when you went to look at what happened, there were very important experimental results like radioactivity. Okay, radioactivity is an example where particles change into each other, which in a purely particle-based theory is hard to make sense of. Like, where did the electron go if it turns into another particle, right? Of course, it went into other particles, but it's hard mathematically to describe that. And when people like Enrico Fermi came along and tried to describe the decay of the neutron into a proton, and an electron, and an antineutrino, he basically said, we should think of these particles as excitations in fields also. And so the first step was to unify particles and fields into just fields. Now, there are two different kinds of fields, as it turns out, one of which ends up looking like particles, and the other one ends up looking like fields. The particle one are called fermions, after Fermi. The field-like ones are called bosons, after Bose, an Indian physicist who corresponded with Einstein. And these two different kinds of particles are absolutely central to physics today. Most of what we think of as matter is fermionic particles, like taking up space, electrons, quarks, neutrinos. Most of what we think of as forces come from bosons. They can pile on top of each other. So they give us light for photons or gravity for gravitons, etc. And amazingly, all of these forces that we know about are related to symmetries in some deep way. I'm going to try to give you the shortest possible thing here because we can go into it in more detail later. But this was a discovery, you know, again, our paradigmatic force theory that we thought we understood was electromagnetism, going back to Maxwell. And that theory has a deep symmetry in it called gauge invariance. And people knew about it. They didn't know whether it was important or not. So in the 1950s, Yang and Mills, two physicists, suggested generalizing the gauge invariant symmetry of Maxwell's equations to bigger kinds of symmetries. And it made predictions that were obviously untrue. So no one really knew what to do with this. Like mathematically, really, really interesting and compelling, but clearly ruled out by the data. So over the next couple decades, people figured out how to tweak the theories so that those theories that Yang and Mills invented are in fact very compatible with the data. And it turned out to be very, very difficult because there's the weak interactions and the strong interactions. Electromagnetism descends from a higher energy version of the weak interactions. They all act differently for very different reasons. Gravity doesn't fit in. There's still plenty of things we don't understand, but we do have a predictive model for how all of these known particles and forces behave. We have the fermions, which are electrons, muons, taus, plus their neutrino cousins. And then we have the quarks. We have 6 quarks, up, down, charmed, strange, top, bottom. And then we have the forces, electromagnetism, weak, strong, gravity. And they all play together. There's the Higgs field that is changing the properties that the other particles have. So it's very intricate, very ugly, and exquisitely adapted to fitting all of the experimental data that we have.
I know that this is exceedingly basic for you and repetitive, but on a very superficial level, everything you just said about the standard model seems to suggest that it is about fields and particles, or forces which are also cashed out in terms of fields and particles that come out of them. And hence that, again, facially, these are the fundamental objects of the theory. So can we just make explicit again why this is the wrong way of viewing the standard model, and that it is the wave function that is the fundamental ontology of the theory?
You're such a philosopher, Robinson. You're never gonna escape this way of thinking about things. It's not wrong to talk about either particles or fields, and I make that point in the book. If the question you ask very precisely is what is the fundamental ontology, then the answer is the wave function, the quantum state, a vector in Hilbert space. But if you ask a different question, which is how do we best understand what's going on? What is the most convenient and useful and informative way to talk about what's going on? Then clearly it's fields and their excitations, the particles. That's okay. The fields and the particles are sort of an emergent way of talking about it, or even a little bit more precisely, they're kind of like coordinates, right? When you have coordinates on a manifold, it's very, very useful to have coordinates. If you want to do general relativity and talk about the precession of Mercury, the first thing you do is choose a coordinate system to work in. But that's not fundamentally what matters, right? It's just a certain choice that human beings make to make their lives easier. Same thing is true with the fields of the standard model. They are a super duper, very useful way of talking about this quantum theory that is fundamentally defined by a wave function obeying some equivalent to the Schrödinger equation.
When people hear from people like me who repeat this over and over again, that the standard model has been confirmed to something like 14 decimal points, it's our and as you've said, it's our best empirically confirmed theory. What exactly does this mean?
Well, you can't quite say, I would like to be able to say, but you can't quite, that the standard model is confirmed to like 14 decimal places. Parts of it are. In fact, mostly the parts that are electromagnetism. That's the one that we understand the best. But the weak and strong nuclear forces are confirmed to a few decimal places, but maybe not, to 14. What it means is, for the most part, and this is not the whole story, but this is the most important part of the story, we scatter particles off of each other. We collide particles together and we see what comes out. This is the paradigmatic thing that you're taught to do when you take your quantum field theory class. You imagine setting up an initial configuration where two particles are coming in to hit each other. They hit, they convert, because they're really waves in a field, and those waves are going to set up vibrations in other waves, so they go out as other kinds of particles. And there's a mathematical description for what happens using Feynman diagrams. And Feynman diagrams are this beautiful way of calculating the probability. Given some initial state coming in, what is the probability of observing different states going out? So either metaphorically or literally, that's what we do. At a place like the Large Hadron Collider in Geneva, we literally do that. We collide particles together, we predict what's going to happen using Feynman diagrams, we see what comes out, and we compare that to the predictions. That's where we get to say the standard model is so enormously successful.
But you also in the book you mentioned that, I mean, it has some serious weaknesses. And I'm getting toward, I mean, after we talk about this, what comes after the standard model, but what are some of the weaknesses that it has despite being so well confirmed?
Well, I think that there are two kinds of weaknesses in the standard model. And, well, let's be fair. Let me be super duper fair. Three kinds of weaknesses in the standard model of particle physics. Okay. One is that gravity is not complete yet. We have a theory of gravity, general relativity, that is very, very good, but there's even a quantum theory of gravity which works, here in the solar system. As long as gravity is not that strong, we have quantum gravity, no problem. But we don't have a complete, finished, final theory of quantum gravity, so we don't completely understand black holes or the Big Bang or things like that. Now, usually physicists deal with this just by not including quantum gravity in the standard model of particle physics. Frank Wilczek has advocated for grouping them together and calling them, did I say quantum field theory? Not including gravity in the standard model of particle physics. Frank Wilczek says we should call them the core theory as sort of a version of the standard model that does include gravity. But still, you would like to understand gravity better than you do. The second problem is that there is empirically something very, very big that was not part of the standard model, namely dark matter in the universe. So, and maybe there's other hints from like astrophysics and whatever, that the standard model is not quite up to the task of explaining observational data from astronomy, right? It explains very well observational data from laboratories here on Earth, but out there in the universe, it's a slightly different story. So almost everyone believes, although we're not 100% sure, that you need to go beyond the standard model to account for dark matter in the universe. That's the second problem. And then the third problem is, even though the theory fits the data, it does so at the cost of a weird set of fine-tunings that we don't understand. By which I mean, the standard model has all these different fields in it, and these fields interact with each other in different ways. And those interactions are generally parameterized by some coupling constants. And most of the coupling constants are very well behaved. They're, like the fine structure constant of electromagnetism is approximately 10 to the minus 2. It's, slightly small number, but it's not crazy or anything like that. But then there's these other numbers, like the ratio of the mass of the Higgs boson to the Planck scale of quantum gravity. That's 10 to the minus 16. That's a weirdly small number. And the ratio of the vacuum energy, the energy in empty space, to the Planck scale to the fourth power is 10 to the minus 120 and something. That's a crazily small number. And we don't know why. There's other small numbers, like there's a parameter in the strong interactions that governs violations of a symmetry called CP. You've probably never heard of any of this, but there's a number that should be between 0 and pi, and we measure it as less than 10 to the minus 10, and nobody knows why. So there's these weird features of the standard model that in order to fit the data, you have to take numbers that you would have guessed would have been 1, 10 to the minus 1, 10 to the minus 2, and set them to much, much smaller values. Those kind of fine-tuning problems hint to most of us that there is physics beyond the standard model that helps us make sense of these problems, but we don't know what it is yet.
Yeah, just to see if I can categorize these two types of weaknesses, would it be fair to say, and again, totally shoot me down when and if I'm wrong, that something like dark matter could be fit into the standard model without having to totally revise it or find deeper physics, whereas the issues with fine tuning, like you just mentioned, that we don't understand, do in fact point to there being some deeper physics?
Well, dark matter does not fit into the standard model. You can come close. There's a couple of candidates for dark matter that you could argue are part of the standard model, namely massive neutrinos or black holes from the early universe. But in both cases, the standard model as it is not up to the task. You need to modify the standard model in some way to either produce black holes in the early universe or to give neutrinos or to create a kind of neutrino that can be massive enough to be the dark matter. But as we understand it right now, all of the particles in the standard model have been ruled out as candidates for dark matter.
Okay. And before we continue talking about possible successor theories, I just wanted to clarify another comment from your book that I wrote down and was curious about. So, referring to the standard model, you wrote, after describing some of these weaknesses, that's okay. Nobody expects it to be the ultimate beautiful theory of everything, if there is any such thing. And it was this, if there is any such thing, that I wanted to press you on, because it seems to, one, suggest maybe that you're skeptical of either our ability to completely understand the universe, or two, that there is some potential regimentation of all the physics out there.
Well, there's potentially lots of things. Remember, my point in this book is to only say things that we are pretty sure are true. So we would like there to be a single beautiful underlying unified theory of everything, but we don't know. So I can't just say, oh, I promise you there will be. I mean, I have no right to say that. There's a certain way that physicists think and theorize, et cetera, but we should admit the boundary between what we know and what we don't know. Certainly, we have no right to say that there is a beautiful final theory. I mean, maybe the final theory is going to be ugly, right? Like, how do I know what it's going to be? So I'm just being honest about the difference between what is more or less established by experiment versus what we're hoping for.
One of the potentially beautiful final theories of everything that I said that you gave an honorary mention to in the book is string theory. And one of the things that proponents of string theory point to as a strength is its potential to solve this fine-tuning problem, namely by positing the existence of something like 10 to the 500 other universes in a big multiverse, each of which instantiates a different physics, one of which corresponds to different permutations of these constants, these 17 free parameters in the standard model of particle physics. And I am wondering, just facially, why you don't consider, well, you wouldn't be a string theorist unless you worked on string theory, but my understanding is that you don't endorse string theory at this point.
Well, it's not that I endorse it or not. We just don't know. I think that string theory is certainly the leading candidate for quantum gravity that we have right now. That's why it gets a mention in the book, and other theories don't. But we don't know. And it turns out to be very, very hard to take ideas from string theory and make specific, surprising empirical predictions with them. It's amazingly successful in many ways. There are many ways that string theory could have failed, and it didn't. I mean, that's why, it was invented in the late 60s, early 70s, and people didn't really jump on the bandwagon because they thought, it'll eventually fail at some point. And then in the mid 80s, John Schwartz and Michael Green showed that it didn't fail in some of the most obvious ways that you might have thought that it did. Quantum gravity is hard, and string theory is a consistent theory of quantum gravity, which is pretty amazing. The question is it the right one for the real world? And that we just don't know right now.
Granted that you said it's our leading candidate for quantum gravity, and that might not be a good thing if you don't think the playing field is particularly talented. Does that mean that you think it is our current best candidate for explaining the fine-tuning problem?
Well, that's a different question. String theorists themselves have opposing views about this idea of the cosmological multiverse and the landscape, etc. It is, by the way, it is an example historically of maybe the only time that an experimental result had a dramatic impact on the course of string theory. String theory has so far had no dramatic effects on the experimental results, but at least one way it happened in 1998. In 1998 was when we discovered the acceleration of the universe, which is most easily attributable to vacuum energy, the cosmological constant. And a lot of string theorists, before that happened, again, not all, there wasn't a consensus, but the majority view was you literally cannot have a positive vacuum energy in string theory. People wrote papers trying to argue for that. And then nature says, well, I have a positive vacuum energy. And string theorists were forced to confront that. And thinking about that problem is ultimately what led them to realize, if you allow this and you allow that and you do this kind of construction, then you can get a solution with a positive vacuum energy. The problem is you get 10 to the 500 of them, and you don't know which one you're in. So maybe you're in all of them somewhere in the universe, and we just happen to find ourselves in one. Even that is not completely accepted within the string theory community. String theory is hard, and we have no experimental guidance. So we just don't have very strong convictions about what is consistent or inconsistent with string theory right now.
This points the way to another deeper question about just how physics is, or theoretical particle physics is supposed to progress at this point, because you said that this is the one experimental result that played a role in the development of string theory, and that, of course, is one of the biggest charges against string theory, is that it doesn't have experimental confirmation. But my understanding is that one of the problems with this, or one of the reasons this is the case, is that phenomena related to quantum gravity are only really salient or manifest themselves on very small distance scales around the Planck scale, or in places like the center of black holes, where we either don't have any access to, or we can't generate enough energy to get access to. And this raises the question, in the absence of experiment, which has historically guided a lot of the development of physics, how is physics supposed to progress beyond the standard model?
Slowly. We can only take what nature gives us. There's something that I do like to point out, which is that the first half of the 20th century was just astonishingly productive for revolutionary discoveries in physics, from special relativity to the existence of atoms, to quantum mechanics in all of its various guises, quantum field theory, radioactivity, but then general relativity and special relativity and the expanding universe and the Big Bang. All of these are from the first half of the 20th century. And we got spoiled. The whole second half of the 20th century was just spent having fun cleaning up what we discovered in the first half of the 20th century. And maybe we did it very effectively. So we're in this very strange position right now where our theories are really, really good. We have these fine-tuning problems, et cetera, but to a good approximation, our theories explain all of the data that we have. And when they don't, like the dark matter, the data are just too kind of simple to really give us a lot of guidance as to what direction to move forward in. It's not that we don't have good theories of what the dark matter could be. We have too many. We have far too many, and it's hard to decide between them. So, there's a couple of different strategies here, and it sounds sort of unhelpful, but one strategy is just keep plugging. Keep working at it, push experiments to higher energies, push cosmological measurements to greater precision, push your theoretical predictions and your model building to ever more clever ideas, and maybe we'll get something. We don't know. Eventually we will, but we don't know when it would be. And then the other strategy, which is what I currently favor for my own personal self, is to take a breath, to step back, and to think deeply about the foundations of these theories. Is there anything that we've glossed over? Remember, we told the story of quantum mechanics and how physicists are like, all right, show me the money. What can I do with this interpretation of quantum mechanics stuff? No, all right, I'm going to move on and do other things. Well, now there's not a lot of other things to be done. In the 40s, there was. Now we're still stuck with the same problems we had 10 years ago and 20 years ago. So it makes perfect sense in my mind to step back and think, okay, quantum mechanics, quantum field theory, fine-tuning, naturalness, the anthropic principle. Let's try to really think carefully about what all of these mean. Maybe they will shed some light on these problems that we've had lurking around for decades now.
Talking about this strategy of stepping back and thinking about the foundations, I have read this or said this a number of times so many times that I should have it in my memory now, but your title is the Homewood Professor of Natural Philosophy at Johns Hopkins. Is that right?
It is. That's right. I picked it.
Okay, perfect. So you were prior to that at Caltech as a research physicist. Is this one of the reasons that motivated your move to a philosophy department? You just wanted to be able to think more about foundations because you think that's where one place, at least, where the action is moving forward?
Yeah, well, what I wanted was to be in both a physics department and a philosophy department, and that's what I got. There's no natural philosophy department, just so anyone knows. It's just my title, even though in practice I am in both physics and philosophy. And that's what I really thought was, to me, the interesting intellectual place to be. And very, very few places will let you do that in any productive way. There's plenty of philosophers who think about physics. There's some, not plenty, physicists who think philosophically, but almost never officially, almost never in a way that that's your job title. So I'm one of the very, very few people in the country whose job title it is to do both physics and philosophy. And I think that's a very, very promising place to think about some of these deep questions. Yeah, absolutely.
I'd like to ask then about natural philosophy. And the last couple of chapters in Quanta and fields cover how chemistry and the macroscopic world emerge out of physics. And though you do point out that to really do justice to chemistry alone would take 100 volumes, but I wanted to take this a bit further, though, and ask some other philosophical questions. But first, how do you gloss the philosophical program of naturalism?
Well, it's a good question. I taught a course last semester in the philosophy department on naturalism, and the students kind of liked it because they said, all the individual ideas that we talked about had for the most part been brought up in other philosophy classes, but had never been sort of put together in this way, right? Because you need to talk about epistemology, you need to talk about foundations of mathematics. Are mathematical things real? Is that part of your naturalism? You have to think about moral and ethical philosophy. Or is morality real? You get to think about physics and emergence and complexity and all these things. So I think that naturalism is just sort of a very, very rich source of philosophical ideas. That's not surprising, not my original thought, but thinking of it, as naturalism is actually doesn't happen as much as you might think in the philosophy community. So I think doing that opens up some doors to connections between different sets of questions in philosophy. Justin Clark Doan at Columbia is a philosopher who I had on my podcast, Mindscape, and he works on morality and mathematics, the parallels and non-parallels between the foundations of moral theories and the foundations of mathematical theories. And so to me, that's quintessentially natural philosophy, like thinking about the natural world, but taking seriously the challenges of it. Just to say, okay, it's the natural world, we're going to do science on it and learn about it, leaves a tremendous amount of philosophy still to be done.
Maybe to dig into some of these areas that you taught about in this class in particular, what might a class on a naturalist epistemology look like? So for our listeners, again, epistemology is the study or philosophy of knowledge.
There's famously a paper by Quine called Epistemology Naturalized, where he actually, people don't agree on what he was trying to say in that paper, so we had fun sort of parsing it. One extremist view of what he was trying to say in that paper is, rather than studying what exists and how we learn about it, rather than thinking about how we should learn about what exists, we should study how people actually do generate impressions about what happens in the world. I think most people are like, well, let's do both of those things. I don't think we need to pick one or the other, but it's an interesting, claim that we should just be studying how people learn rather than sitting back in our armchairs and proclaiming how they should learn. But then there's also questions about, as we were talking about before, realism, structural realism versus ontological realism. People like Nancy Cartwright have argued that you're not going to find one unified theory of physics. It's going to be a patchwork that describes different domains. Even within physics, people like Phil Anderson in his famous paper, More is Different, has really advocating giving some ontological heft to the higher emergent levels, things like that. So we read those papers. We read Dan Dennett's paper on real patterns. There's, are tables and chairs real, right? You can be a realist about electrons and protons and neutrons. Does that imply you should also be a realist about tables and chairs? These are all perfectly good questions for naturalized epistemology.
Well, since you mentioned at the outset of our conversation, I think what you said was that physics speaks the language of math. And because the book relies so heavily on equations in a way that other books don't, I think it's worth talking more about the relationship between math and physics. And how do you, at this point, granted that, you're not a dedicated philosopher of math, which people like Justin are. How do you try to cash out mathematics naturalistically?
Man, I don't know. The philosophy of math is the thing that bugs me the most, honestly, that I don't have any strong feelings about. I have what I want to believe, which is kind of a nominalism, an if-thenism about mathematical results, that I can sort of invent any system of axioms I want and then prove theorems based on those axioms. And the theorems that I prove have the kind of truth that they have is, well, if the axioms would be true, then the results would be true, right? But there are other people, like Justin would say, look, you're doing physics. You're talking about the standard model of particle physics, and your physics works, right? Like you think that your theory is going to keep working. So that only makes sense if you think there's some fundamental consistency in the mathematical tools that you're using to describe that theory. But guess what? You can't prove consistency. Professor Gödel showed that to us a long time ago. So probably you're assuming that your mathematical tools are consistent. And if that's true, how do you know? How in the world could you know that they're consistent if you don't think that they latch onto something real about the world? And I honestly don't know what to say about that. I want to say, well, I want to avoid the question by saying, look, tables and chairs I can bump into. They have a causal impact in the world, as do electrons and protons. The number 3 I use to talk about the world, but it has no causal impact. It doesn't, I don't bump into the number 3, either literally or metaphorically. So it's not real in the same kind of way as the physical stuff of the world is. Justin sort of browbeat me into writing one little paper on this, and I called it Reality Realism. And going back to, is the wave function real? I tried to make the case that, and I tried to be very honest. This is not as someone who is a professional philosopher of math in any sense, but someone who has done physics as a working physicist. And my attitude is, reality is real. The real world is real, the physical world. And we discover it by doing experiments, by using empirical techniques, and we describe it using mathematics and various other forms. But it is itself. It is just reality. And we can learn about it, but don't try to give extra things the status of reality other than the physical world.
Speaking of Quine, who you mentioned with the epistemology naturalized paper, he was also a nominalist at the beginning of his career, but then he reluctantly began to admit mathematical objects into his ontology of the universe because of what have become known as indispensability arguments for mathematical objects. So what he might have said, though I am reluctant to try to put words into Quine's mouth, are that just as the unobservable electrons and quarks and protons are confirmed by the standard model of particle physics, the mathematical objects that are required or in the formulation of the theories that are quantified over are also confirmed. But this, I take it, is a line of reasoning that you will struggle to resist.
I will struggle to resist it. Number one, it's not obvious that you actually need various mathematical objects versus they're just super convenient. I know that Hartree Field, for example, wrote a whole book about physics without mathematics. Apparently, people bought it thinking that it was like a popular physics book without any math in it, but that's not what it was. It was a very highbrow mathematical logic book. But number two, it's still, it's not the same. The fact that we use math to describe the world proves that even if it were true, all that proves to me is that we need math to describe the world, not that the math really exists. Not that the mathematical objects really exist in the same way. So, and again, and what makes me think about this is like, what about, the continuum hypothesis? So here is, for those of you who don't know, conjecture or a hypothesis in the foundations of mathematics. We know on the basis of standard arithmetic and number theory that the number of integers is infinite. The number of real numbers is also infinite, but Cantor proved that the number of real numbers is clearly bigger in a very real sense. It's a bigger infinity than the number of integers. The question is, are there any other infinities that are in between the set of real numbers and the set of integers? We don't know. And well, it's not that we don't know. You can posit that as an axiom and build perfectly good mathematical structures on that basis, or posit that it's not true as an axiom and build perfectly good mathematical structures on that basis. So is that number that is in between the cardinality of the reals and the cardinality of the integers real? I don't see how an argument like Quine's would affect that.
Problems like this point some philosophers of math, like Joel David Hampkins, currently at Notre Dame, to posit this massive mathematical multiverse in which there are different set theoretic universes where these different systems of axioms sort of describe the set theoretic universe in question. So there are universes where the continuum hypothesis is settled one way, universes where it's settled another way.
Yeah, and I'm extremely sympathetic to that. That makes sense to me. But
you're sympathetic to it? So you want to admit that there are these universes of mathematics out there?
None of these universes are real in the sense that the real physical universe is there, but I want to be a pluralist about the foundations of mathematics. I don't think you're going to find the right one. If we talk to someone like Tim Maudlin, who again is a philosopher of physics, not of mathematics, but he will say, no, there's something called the integers. And you can prove that your axiomatic system allows for different models, the standard integers and the other integers, but that just means that's because there are truths about the integers that your axioms will never capture, but there are still truths about the integers because the integers are real, he would say. And I think that's what Hampkins and I would want to say, no, that's just not actually the case.
I think actually Joel would be much more like Gödel, who believes that it's not a physical thing, but there is a set theoretic universe out there. I mean, when one of the times that Joel and I spoke, he picked up a mug on his desk and he said, "This mug is very perplexing to me. Is it a field? Is it a wave function? Is it protons? I really have no idea what it means for this mug to exist. But on the other hand, I know so much quite concretely about the empty set, about zero, so that I am very certain about the empty set's existence, which is kind of confusing in a way, but he's much more confident about the empty set's existence than he is about the mug. So I think he's much more concrete in a sense. I mean, these are confusing issues to talk about, but he's much more invested in the concrete existence of these.
So I'm going to have him on my podcast. He's already scheduled, so I'll talk to him about these things. But you can fail to understand all the details in the coffee mug, and you can understand everything there is about the empty set. I'm still happier if you tell me you're going to throw the empty set at my head than if you tell me you're going to throw the coffee mug at my head.
Well, moving on from the philosophy of math, morality is a particularly, I think, recalcitrant issue to naturalize because people just have these intuitions about it that are hard to disabuse. But how do you think about naturalizing morality?
Well, I think, like math, morality is not out there in the world. I don't think that there are objective moral facts to be discovered. I don't think that there are experiments you can do to distinguish between the truth value of one mathematical moral hypothesis and another one. I'm a constructivist. I think that morality is something that human beings create. And which kind of morality we should create, I'm much less certain about. I have much more firm convictions about meta ethics than about ethics. But I think once we agree on the meta ethical principles of constructivism, et cetera, then we can probably get together and hash out some ethical principles that we can agree on.
Does this allow for how does this allow for disagreement between or settling disagreements between people who have constructed different moralities? Does it preclude these sorts of
they're probably not
agreements?
going to agree. And guess what? In the world, they don't. That's just correctly describing what happens in the world. This idea that it must be the case that two perfect reasoners, rational humans, must agree on every statement they make, I think has zero evidence for it in the real world.
Mm-hmm. So there's no fact of the matter for you about who is right or wrong.
That's right.
Now, there are some philosophers, I think, that they are labeled intuitionists in that they think, and correct me if I'm wrong here, but they think that we have something like a sixth sense where we can perceive moral properties. And so if, let's say, I'm walking down the street and I see somebody kick a cat, I just perceive something wrong just as readily as I perceive that the sky is blue or feel that I'm in pain or something like that. I have a sort of, direct access to this. How do you respond to these sorts of moral intuitionist claims?
I can't even imagine that the people who make these claims don't already know what the response is going to be. There's a analogous claim in theology, right? That there's a sensus divinatus, that certain people can sense the presence of God in a kind of physical sensory apparatus, but other people just lack that sense. So, okay, that's a perfectly good hypothesis. Here's my hypothesis. No, you just made that up. You're just translating your feelings into some, reified thing in the world. And I'm under no obligation to go along with you there. Sorry.
Thank you for letting me put you in the philosophical hot seat on all of these issues. I think as we finish, maybe it would be good to return to Quanta and Fields and some of the many, perplexing puzzles and myths that I think the book helps clarify. And one of these is a topic of enduring puzzlement, and that is entanglement. And I have a few different questions here. One, what are some common misunderstandings of the phenomenon? Maybe that's where we should just start.
Well, I think, entanglement arises directly from that statement we made long ago that when you have a quantum system, you do not have separate wave functions for each part of it. You only have one wave function for the whole thing. And the job of the wave function is to make predictions for observational outcomes. So if that's all true, then it could be the case that if you predict the outcome for one thing and another thing, particle A and particle B, there might be correlations or connections between those measurement outcomes. So I don't know what I'm going to see when I ask what is the spin of particle A. And I don't know what I'm going to see when I ask what is the spin of particle B, but I know they're going to be opposite. So then that's entanglement, and it tells me, were I to measure particle A, I have no idea what I'm going to observe, but as soon as I do, I know what the outcome is for particle B. And this bugs people because how does particle B know what its outcome is supposed to be? It could be light years away, right? This bugged Einstein. This was the point of his famous EPR paper in 1935. And so I think that people get the idea, and also from the word entanglement, that entanglement is somehow a force, that it's somehow an influence, right? That you can sort of tug on it, that, there is some mystical thing that connects all of us through quantum entanglement. But really, it's a very, very precise mathematical thing. You can make predictions about the measurement outcomes for one entangled subsystem based on the measurement outcomes of another entangled subsystem. That's it. You cannot use that to send information or to have any influence or anything like that. So in particular, because I don't know what measurement outcome I'm going to get when I look at the first particle, I can't force the other particle to have any particular state at all. So I can't push it around by doing anything over here. So I do think that if we had discovered quantum mechanics before classical mechanics and we had really internalized the lessons of quantum mechanics, we wouldn't call it entanglement. Because entanglement suggests that we start with two subsystems and then there's some mystical force between them. As we said, the whole quantum picture says there's only one system, the wave function of the universe. And what's interesting is that under the right circumstances, we can profitably describe it as different subsystems obeying certain kinds of rules.
I think this connects to the inability to send information, but can you clarify for me the distinction between maybe a causal connection between the two entangled particles and then a statistical correlation between them?
We don't know what's happening between them. That is one of the things that is, you're going to get a different answer depending on your favorite version of the foundations of quantum mechanics. Okay. So in Everett, what you would say is that when I measure one particle, particle A, Alice's particle, and Bob's particle, particle B is way over there, nothing happens over there necessarily. It's going to depend on your description. Maybe something happens, maybe something doesn't. But the point is that the wave function of the universe doesn't undergo any dramatic shift right away. Right where you are, you branch into two possibilities, right? On one, Alice gets a certain answer. On the other, Alice gets a different answer. And then, and this is very complicated, and I don't like it, and it's hard to explain, but there are two different ways of describing what happens next. One way is these branches, one which Alice says spin up and the other one Alice says spin down, instantly propagate across the universe, simultaneously everywhere. And so now there is a branch on which Bob gets spin up and a branch on which Bob gets spin down. And the rules of quantum mechanics are that if Alice got spin up, Bob got spin down and vice versa. But there's another way of doing it where the branching sort of stays inside the light cone. It propagates out at the speed of light or less. And all of the light cones sort of match up together in a nice way in the future. And someone like David Wallace would argue in favor of that. The truth is it doesn't matter, because this idea of branches is much like tables and chairs, a higher level emergent phenomenon. It's a way that we human beings describe what's happening, but the wave function of the universe, all it ever does is obey the Schrödinger equation. Laplace's demon doesn't know about branches of the wave function. It doesn't know about measurement collapses or any of those words. It just has a wave function that obeys the Schrödinger equation at all times. So, again, that's the way that I would explain it using many worlds. It sounds kind of contrived and hard to understand, but that's because we are trying to force our human intuitions onto what the wave function is doing.
Since this is a place where the foundations are concerned, does that mean that it's a place where, at least the way that physics and philosophy departments are currently set up, it's a place where philosophers are more interested in getting their hands dirty than physicists, and physicists have just kind of moved on and are happy with the predictive capacity of the theory. But at this point, you think it is answering these questions that will be very helpful with moving the standard model forward.
Well, it's interesting because, of course, if you have some question that is physics adjacent, like the foundations of quantum mechanics or like the existence of black holes in the 1950s, but that you can't do any experiments on, physicists will tend to ignore it, and they can happily go on and just do other things. But then that situation can change historically, right? In the 1960s, we realized that quasars are powered by black holes, and suddenly people became very interested in them. Also in the 1960s, John Bell proved his theorems. He proved theorems about the different predictions between a local theory and a non-local theory like quantum mechanics. And that made it an experimentally accessible question. And so people did the experiment and they just won the Nobel Prize a couple of years ago. So physicists are very interested now because there's an experiment you can do. Of course, the experimental result was exactly what Schrödinger would have predicted back in the 1920s. It didn't change our idea of quantum mechanics, but as long as you can do an experiment, they're happy. Having said that, because physicists have ignored the foundations of quantum mechanics for so long, even the Nobel Prize press release botched it. They gave the wrong explanation for what was going on because they didn't really understand what they'd just given the Nobel Prize for. So physicists still have a long way to go to understand these foundational questions.
Moving on to another of these myths that I wanted to address, and this one actually came up in an episode that I did with somebody I know you've spoken with, Chiara Mingarelli at
Sure.
Yale now. But the question is, why isn't there just one electron? And Chiara Mingarelli, she mentioned this almost like it was a fact. And I was surprised by that, just because I think you mentioned that this was something John Wheeler suggested to Richard Feynman. But I'm wondering if this is really, to use the word again, sort of an enduring myth within physics communities, and why there isn't just one electron out there.
Yeah, I think it is a little bit of an enduring myth, but also, physics is a big field. Chiara is a brilliant physicist doing gravitational wave astronomy, and you're asking her a question about quantum field theory, so she's going to give you the myth. The deeper answer is no, there's not just one electron, there's a field. There's the electron field that has vibrations in it. The reason why every electron has the same mass and charge is because they are all vibrations in the same underlying field.
But what would be the intuition behind there only being one electron in the first place?
Oh, that's a good question. And that it actually did make sense. Like in the modern way of putting it, a little bit anachronistic because the modern way of putting it didn't exist back then. But you can have things in quantum mechanics, in quantum field theory, like an electron and a positron, the anti-electron. They come together and they annihilate and they spit out two photons or something like that. So if you think about that process, there's an electron and a positron coming in, no electrons or positrons coming out, just photons, right? But in the Feynman diagram that you would draw for this kind of process, there's one line that sort of contains electric charge. It contains electric charge, negative charge for the electron, but then you have to connect it to the positron because electric charge is conserved. And now the positron can be thought of as an electron going backward in time, mathematically. It's not really going backward in time, but the mathematical description of a positron is just a time-reversed electron. So if you see I have one time-reversed electron and one electron, and then they turn into nothing, Wheeler says, well, maybe I can think about that as one electron traveling forward in time and then continuing its journey backward in time, identified as the positron. And maybe that one electron just zigs back and forth to beat the band throughout the history of the universe. That can't work because electrons can annihilate into things other than photons and annihilate in ways that do not involve positrons. And so the number of electrons minus positrons is not actually conserved over time. But it's clear why it was tempting, and it inspired Richard Feynman to help derive the whole Feynman diagram way of talking about these things.
Maybe this wasn't mentioned in your response, but this line of reasoning, does it apply to all particles? Was Wheeler suggesting that there's only one of every particle, or this is just particular to electrons?
I think back in the day, for very good reasons, they were focusing on electrons, positrons, and photons. So this is the 40s or 50s, right? So QED, quantum electrodynamics, is the theory that just has electrons, positrons, and photons. So that's what they were thinking about. They didn't know about the standard model of particle physics as we currently understand it. I mean, if Wheeler had thought about it a little bit more, he would have known that a neutron can convert into a proton, an electron, and an antineutrino. So there were 0 positrons and electrons, and now there's 1. So it couldn't be that there's only 1 electron in the whole world.
Then this is a myth that I guess I didn't realize was a myth until reading Quanta and Fields. But this myth is, you hear all the time, is that atoms are largely empty space. And so consequently, we are largely empty space. And this is kind of
Total
how
myth.
I've been looking
Yeah.
at the world. So
Yeah.
what, again, maybe this is the best way to ask the question. Why is this intuition, well, maybe it's not an intuition, why is this factoid out there, or this myth out there, and then why is it wrong?
Well, it's out there because people don't really, deep in their bones, want to accept quantum mechanics. They want to think of the electron as a little dot that is orbiting around the nucleus of an atom like the Earth orbits around the sun. If you pressed them, they would say, oh, no, of course, I don't believe that. But that's exactly what they believe if they're saying that that atoms are mostly empty space. They just mean this in the same way they mean the solar system is mostly empty space. But the solar system is not like an atom. The solar system would not make a solid if you put many, many solar systems together. It would just squish down, right?
Mhm.
Atoms are different. And the reason why atoms are different is because electrons are not little dots. They are wave functions. And those wave functions take up space. And that's what makes matter solid.
Okay, and again, when we're saying that electrons are wave functions, this is us speaking figuratively, maybe in the second dimension, because one, we've already said that there's only one wave function, and then two, electrons on this quantum field theoretic picture are just fluctuations in fields. So there's okay.
So all of that is true, and all of it is fine. So this is one of the things that makes learning physics very, very hard. That we say, okay, if you're really, really rigorous and careful, you have to speak this way. But then on the very next page, you're like, we're not going to be rigorous and careful. We're going to talk in ways that makes our life easy. So yes, electrons are really vibrations in the electron field. But okay, once you've learned that, you're allowed to talk about electrons now. You don't have to keep saying that motto over and over and over again. You've understood what electrons are, but there are electrons. And number two, yes, there's only one wave function, but in very wide varieties of circumstances, it makes perfect sense to talk about things as if they are separate things, like the table in front of me and the coffee mug in front of me. These are two separate things. It's true that deep down in quantum mechanics, they are described by the same wave function, but come on, you're not going to stop me from talking about them as two separate things.
And the last of this doesn't really qualify as a myth, but it's something that's always bugged me. And this episode, I think, will be coming soon after one with Nick Bostrom, where we didn't speak so much about the simulation hypothesis, but his recent work on utopia. But are there things that you would suspect or expect to see in our physics that would be indicative of our being in a simulation? Or to put it in other words, are there things that we see in our physics that come close to ruling out our being in a simulation?
I don't think you can rule it out, but I don't see any evidence for it either. I don't see anything at all that is better explained by saying we live in a simulation than we don't. If we saw, occasional miraculous deviations from the known laws of physics, I might feel different, but we don't. If we saw some fundamental resolution limit, or if our universe was very, very small and clearly optimized to conserve some kind of resource, then I might see a different point of view. But just as a Bayesian with certain priors, nothing that I see about the universe increases the likelihood that it's a simulation for me.
Okay, this is really the part about there being some fundamental resolution limit is quite striking, just because I know that many of the quantum theories of gravity are predicated on an assumption that space is fundamentally a lattice, like causal set theory, which I mentioned earlier, or Stephen Wolfram's Rulliad, space is discrete. And a lot of this comes from really ancient intuitions, like with Zeno's paradoxes, and also, some unease with fields and space being continuous. That just doesn't sit well with some people. So one, I guess, if causal set theory or something like the program of the Rulliad were verified in some way and space was shown to be a lattice, would that lend credence to you to the idea that we are in a simulation?
Well, the causal set theory and Wolfram's theory, two things about them. Number one, neither one of them is a very good theory of quantum gravity, so I'm not paying a lot of attention. But number two, they're very different theories. Causal set theory is still based on quantum mechanics, and quantum mechanics is based on the continuum. Schrodinger's equation and Hilbert space and time and all those things are absolutely continuous in quantum mechanics. So you might quantize a lattice, but the quantum theory, the wave functions themselves still live in a continuum. Wolfram's theory is different. That is fundamentally discrete, but it's also, as far as I can tell, very, very far away from matching the real world. So again, I'm just not that moved by that. If something like that turns out to be true, call me up again later.
Do you have, I mean, I mentioned a lot of people have this intuition against the continuity of space motivated by such current concerns as Zeno's paradoxes of motion. Do you have any concern about fields or anything like this on these grounds?
I have a very, very mild concern. Let's put it that way. As we said before, when talking about mathematics and the philosophy thereof, there are puzzles in mathematics, and many of them are traced to thinking about infinity. And if the world were fundamentally finite, maybe those problems would not be there. But like I said, also, quantum mechanics involves the continuum in a very, very deep way. So I did write a paper pointing out that there are versions, you could slightly modify quantum mechanics to completely get rid of the continuum and really base it on a lattice of possible states. In that theory, I don't think that the current version of that theory is quite phenomenologically viable because it would have what we call a Boltzmann brain problem. Most of the universe would spend time close to thermal equilibrium, and there would be small fluctuations around it. And the chances that anyone that looked like us would be such a random fluctuation is very large. Therefore, you have no reason to trust the theory in the first place. And but that's a pretty weak argument because we don't understand this theory very, very well. So I take it as a demonstration of how difficult it is, possible but very difficult, to invent a viable theory of fundamental physics that is truly getting rid of infinity. But if one were to be able to do that, I definitely think that such a theory would have its selling points.
Forgive me this cliched question that I'm about to ask to wrap us up, but I know that Feynman once said famously, if you think you understand quantum mechanics, you don't understand quantum mechanics. And many worlds, which, as we've already mentioned, is your preferred theory or interpretation of quantum mechanics, it gives an account of many of the well-known puzzles like entanglement that we discussed. But are there still any major mysteries for you about quantum mechanics that you would still classify as major mysteries?
Yeah. So, by the way, Feynman never said that. That's a misattribution. What he actually said was in The Character of Physical Law and elsewhere, he said, I think it's safe to say that nobody understands quantum mechanics, which is very different than saying if you think you understand it, you don't. He just says no one does, which is fair if you interpret understanding quantum mechanics as having an understanding that everyone else agrees with, right? Certainly there's no consensus within the field. I do think that many worlds is overwhelmingly likely to be the right foundational approach to quantum mechanics. But within many worlds, there's absolutely important questions. I mean, the most obvious one, I guess there's two very obviously important ones. One is the origin and nature of probability, which I think is mostly under control and understood. The other is the connection to the classical world. Because if you start with this idea that there is only one wave function, Hugh Everett originally titled his paper The Theory of the Universal Wave Function, because that's what he was emphasizing when he invented what we now call many worlds. And that wave function is just a vector in Hilbert space. That's very, very far away from the world of particles and fields and tables and chairs and things like that. So the question of why we think that the world looks like this emergent higher level description is very pressing within many worlds in a way that in other theories it's just not, because they put it in by assumption, right? So there's a bunch of problems that, they don't have to solve in other approaches because they just assume the answer from the start. But many worlds is very lean and mean. There's not a lot of room for tweaking the theory. It's a vector in Hilbert space evolving according to the Schrodinger equation. So you have to learn how to reconstruct the world of our experience, and that's a very, very difficult problem.
Well, Sean, thanks for writing Quanta and Fields, and thanks again so much for coming on the show to talk with me.
Sure, my pleasure.